Hello everyone, my name is Ayush Ojha. Today I am presenting my design and architectural blueprint for the embedded system focused on Smart Home Energy Management System, or in short SHEMS. This project outlines an embedded system designed to bridge the gap between everyday home appliances and intelligent real-time energy conservation. The core problem that we face today is the lack of visibility into appliance level power consumption, which leads to high energy cost and potential safety hazards. The proposed objective for SHEMS is to act as an automated guardian by continuously measuring individual appliance current and voltage levels. The system is designed not just to monitor the power but also to act to disconnect the appliance as soon as the user safety or the budget limit is breached or exceeded. Now let's look at the proposed hardware architecture. This hardware architecture designed by me utilizes ESP32 microcontroller. I chose ESP32 microcontroller as a central processing unit because of its robust processing speed and its integrated Wi-Fi capabilities. For the data acquisition, the design pairs standard ZMPT101B voltage sensor with an ACS712 current sensor to safely monitor the ACS means. Once the logic is processed, the ESP32 drives a 4-channel 5-volt relay module which serves as a physical actuator to switch on or off the appliances based on the energy consumed. This all is powered by a stable 5-volt SMPS. Now, what is SMPS? Therefore, the SMPS, also known as switched mode power supply, is a type of electronic power supply that utilizes high-speed switching components to regulate the output voltage. In embedded system, software timing is critical. Therefore, I utilized object-oriented design to write the software to design the software which is centered around an energy manager class. Now, what does the energy manager class do? The energy manager class processes the sensor's data, compares it with the user specified limits, and then applies the decision logic. The, to guarantee the performance, the execution flow is entirely driven by the timer interrupt service routine, or ISRs. The architecture dictates that the system reads sensor and update the energy values exactly every second. More importantly, it features a strict hard real-time constraint that if a limit is breached, the appliance control action, that is the physical shutdown, must be completed within 500 milliseconds. Here you can see the hardware architecture and software architecture designed by me during the design phase. On the left, the hardware block diagram shows the isolated flow from the sensors through the ESP32 to out to the user interface and relays. On the right, the software architecture outlines the interrupt-driven hierarchy. The top-down design of the embedded system map ensures that the complex tasks like energy computation and Wi-Fi communication do not block the critical real-time sensor sampling. Now let's look at the user interface proposed by me. I proposed a dual interface approach. Locally, the system must use a 16 into 2 graphical LCD so that user can immediately see the status of node on their wall. Remotely, the ESP32 must push this data to a mobile application and cloud dashboard. This remote UI is where the user inputs their specified energy or the budget limit, also can issue manual overrides and receive overconsumption alerts anywhere in the world. Now, what is manual override? The user want a user would want to turn on the appliance even if the limit is breached. Therefore, the user must be given a chance to manually turn on or off the appliance even if the limit is breached or not. Now, while this is just a theoretical design, a robust integration strategy was designed to ensure a rapid deployment. The methodology indicates a step-by-step approach starting from integrating sensors first to verify the raw data accuracy, followed by the relay controllers, and finally the network modules. The sequential testing is designed to isolate and mitigate specific errors such as sensor calibration errors, relay failures, or unstable power supply resets, which comes under the hardware errors and some software errors like interface mismatch, timing delays, or catastrophic memory leaks. Uh, this all must be prevented in order to design an efficient embedded system. Now, finally, let's look at the commercial feasibility of bringing the system to the market. To take this from a theoretical blueprint to a fully tested consumer ready product, including hardware prototyping, GUI development, and a safety validation, the estimated engineering and R&D cost must lie between 30 to 40 lakhs according to the current market rates. However, the true strength of this design lies in its manufacturing scalability because the architecture relies on standard, easily sourced components rather than expensive custom chips. The unit manufacturing cost comes down, you can say driven down to just 1900 to 2100 rupees. This incredibly low production cost means that the system can be sold at a low retail or highly accessible retail price. For the consumer, SHEMS or this system becomes an investment that it literally pays for itself in a matter of months through the reduced electricity bill. My goal with this design is to prove that by turning raw electrical data into an automated action, we can make homes safe, smarter, and much more energy efficient. Thank you for listening to my pitch and thank you for taking out your time. Thank you.